Yes, K also. Let's say 259. Then the same condition, given a delta that exists here not here, it will now depend upon K also. Therefore, there is this condition which will depend upon K also. Then the same A is any subset of delta having more than delta equal. This name you have here 200 will now depend upon Every integer is a sum of 90 fourth powers, etc. That's the problem which is called a balanced problem. Okay? Which has been now completely set. Okay? This is where the circle method has helped really to solve all such problems. And using circle method, then Roth solved the case for k equal to 3. Okay? A little later, of course, then k equal to 3 was also similarly, and then similarly proved k equal to 4, and Roth proved k equal to 4. But for all k, it was proved by somebody. And the proof is not by circle method, it's a pure combinatorics. Okay? And very difficult combinatorics. And then there are other proofs which have come. Okay? Or either doing ergodic method or Fourier analysis and so on and so forth. Okay? Now we know it for everybody. This is one type of problem. Therefore, again, as I told you, the type of questions which we are putting are actually a high school level question. That's all what you are saying. I take a capital N, it is very large. I take a subset A in 1 to N, and I am only assuming that the subset A has, let's say, more than 1 over 100 in elements, okay, a positive density of elements, and I am assuming that N is sufficiently large. And therefore, if N is large and it has more than, 1% of the elements A has, then this A would admit a 3-term arithmetic progression. Okay? Then, there are more things to say about this, but I won't bother. I would concentrate on the other type of problem. Which means, in some sense, you see, already we have said that as far as the terms in arithmetic progression is concerned, a positive density set is good enough. If A is a set of a positive density, it is good enough, it will have a term arithmetic progression. The second problem which you want to look at is the problem which is a little easier than the first one. Earlier we looked at x plus y equal to 2z. Now we are putting x plus y equal to z. Okay? And now we ask the same question. I have a set subset A which is contained in 1 to n is big, which is in some sense which I have to specify. Then will the subset A will have a solution of x plus y equal to z. Is it clear? That's all the question. Okay. Therefore, everything we are still talking about the integers and nothing more. Okay. In the integers itself, we are finding out some really interesting questions. Therefore, the question is, therefore I have a subset A, which is contained in 1 to n, and then I want to know whether it has a solution of x plus y equal to z. Whether I can find out 3 elements x, y, and z such that x plus y equal to z. Okay. Can you think, for example, of some example where A is somewhat big and still it will not have a solution? Okay? Friends. Sorry? Okay, let's do it. First of all, let's do the following. You define your A to be, okay, let's say 1 to 100, for example. Then you define your A to be 51, 52, 53, etc. up to 100. The top half. If I now take the top half, and then it is not possible for me to find out x, y, and z such that x plus y equal to z. And this set has a density half. Because your original thing is 1 to 100, and this set has 50 elements, therefore density half, and still it is not admitting Therefore, this thing is what is called a sum free. That is the word sum free in the dictionary. If there are two elements in the set, the sum is not there. That's a sum free. Okay? Therefore, unlike the earlier case, that's exactly the reason why I introduced the earlier case, where a positive density is already good enough to solve the equation. Here, you have set subsets which are of density half, where you do not see a solution. Okay? And another example for A, which I can give, is for example the set of all odd numbers in 1 to 100. Okay? When you take that, that also we cannot have a solution for x plus y equal to z. When x and y are odd, then x plus y is even and equal to z. Z is okay, it cannot be odd. Therefore, you cannot find out three numbers x, y, z such that x plus equal to z. Therefore, you have a density half, there's no solution. But the theorem is once you exceed that, then it cannot be solved. But that's it. If A has more than n over 2 elements, then it is something. It is not something. It has more than n over 2 elements, then it is always possible to find out an x, y, a y, and a z such that x plus y equals z. Is it okay? This is where we start.
What is capital N here in this here?
Any capital N. No, take any n. Okay? My A is in 1 to n.
Okay.
I take my A in 1 to n and then this A, assume that it has more than half the elements, then it cannot be something. You can find out 3 elements. Okay?
Is it a difficult theorem?
This is trivial. Okay, now that you have asked, and as Lag says, every lecture should have one joke and one proof, and those should not be the same. And therefore, let me give one proof of this at least now. Okay. Therefore, now I want to say, let's say, for example, let's take 1 to 100,000, and this A is a subset. Let us assume, and now let us assume that the cardinality of A is 502. It is little bigger than A. Therefore, now I am saying you take any A, it has 502 elements in 1 to 1000, then I can find out an x and a y and a z such that x plus y equals z. Okay?
And if we took 501,
Also will work. But 500 will not work. You take another set B, which is 1000 minus A. For example, this is 1000 minus A1, comma 1000. This is what the 1000 minus A means. If capital A is the set A1, A2, etc., A3, AN, then of course the 1000 minus A would be that the 1000 minus A1, comma 1000 minus A2. And then clearly the thing of the capital B is also finite. Correct? And now you see A union B plus A intersection B is equal to cardinality of A plus cardinality of B. So this is standard thing in the set T. And the cardinality of A is 502, cardinality of B is also 502, and therefore the right hand side is 1004. And on the other hand, A is Okay, yeah. Both A and B are in 1 to 1000. A is also in the subset of 1 to 1000. B is also a subset of 1 to 1000. Therefore, A union B is also a subset of 1 to 1000. Since A union B is a subset of 1 to 1000, A union B can have at most 1000 elements. Yes. Therefore, there is not a problem. In particular, it shows that A intersection B has to be non-empty. That's the point here. You see, A intersection B is non-empty. What is A intersection B is non-empty? There is an element which is also A, it is also in B. If the element is A, it will look like something like an A8 or something like that. And if it is in B, it will look like 1000 minus some A17. Because all the elements of A are A1, A2, etc. AN. All the elements of B are 1000 minus A1, 1000 minus A2, 1000 minus AN. And therefore, if it is an element of A as well as B, then it has to look like some A8 as well as 1000 minus A17. And therefore, they have to be equal. This is the same element, which means that these two are equal.
Got it.
If assuming 1000 belongs to A, I mean, if the 1000 doesn't belong to A, I take the largest element which belongs to A, let's say 93, and then I can argue with this 993. Therefore, I take the large, and then I still better.
Then you got B, you write it as 993 minus A1 993.
Exactly. B I write as 983. Okay, therefore I take the largest element, which is less than 1000, called 993, and then I write B is 993 minus A1, 993 minus A2, etc. And A intersection B is non-empty. That means that then 993 can be written as the element of A plus the element of B. And after 993 also belongs to. Is it okay? Therefore, once you have the density bigger than half, then you are happy. Is it okay? Now let's make the problem a little complicated. Namely, now we move from our ambient space just from integers to finite abelian groups written additively. Therefore, G is a finite abelian group. Written additively. Okay, that means essentially the group operation is addition. Because group operation has a simple addition. I take such a G. Okay, up to this is it clear? Or I have a mystery here? Okay, it's okay, no? Yeah, for integer. Okay, and now I ask the same question. A, yes, sir, yes, the thing is A is a sum free set if it does not admit a solution of x plus y equal to z. The same definition. The same definition, and therefore you choose x plus y. Okay? And now there's a problem. This question is slightly different actually from the integers. Okay? Now let's take a cyclic group, for example. I take the cyclic group Z over 100. Okay? In this Z over 100, see, if it were integers, I can take 47 and I can take 60, I can take 7 because this is sum free. If it is integers, but if I am looking at the group element of Z over 100, this is not sum free simply because of 47 plus 60 equal to 7. In Z over 100, 47 plus 60 equal to 7, and therefore the number, the elements which would not have been sum free earlier, would not have been the solutions earlier, have become the solutions now. Okay? And therefore, obviously, the sum free set will be much smaller. Okay? Because for the integers you have, but now many things has to be thrown away from that because I can add two large elements and I go to the small element. Therefore, now the natural question which you ask is, what is the subpreset? What is the biggest subpreset in this? Okay? And when you go to the computer and do some computer civilization, etc., then you will find that the biggest subpreset is the middle one, which I will of course explain in a bit detail, but this is the middle one. This is for all cyclic group. Therefore, I should probably explain what it is. Therefore, I take Z over 99Z. Then there is a subpreset which is 34, 35, etc. up to 66. From 1 to 99, of course, this is the middle one term. It's okay? And now is it clear that it is not sum free? It is sum free, essentially because when you add 34 plus another 34, 68, which goes that side, and you go all the way and add 66 plus 66, 66 plus 33, which is also not there. But I cannot put a 67 here, because 67 plus 67 is 35, which is in this set. Therefore, I cannot enlarge it anymore. Okay? Therefore, this subpreset has essentially 33 elements. Okay? Now let me make it a little complicated. We'll have a couple of more examples. 100 is that. Here also it is 34, 34, 34, etc. 66. I cannot go beyond that. Because I cannot put 67 again. Because 67 plus 67 equal to 34. Which I have already included. Therefore, this is all what I can do. And therefore, this has essentially 33 elements. And Z over 101 Z. Here I can do something. I can put 34, 34, 5, 36, etc. up to 67. Because now 67 plus 67 is only 33, which is not in that group. Okay? And therefore this has 34 elements. Okay? Is that clear? Okay? This is for some preset. And therefore, theoretically, what do you get? You get essentially the number of elements is Z over N is N by 3 if 3 divides N equal to N minus 1 by 3 if N is you all know what is congruence, no? When I write N equal to 1 mod 3, you understand what it is, no? Clear? N equal to 1 mod 3. And equal to N plus 1 by 3 when N congruent to 2 mod 3. Okay, this will be the exact number which you are getting. And therefore, I have already produced a sum-free set of this cardinality by just taking the middle one third. By just taking the middle one third, I have already produced a sum-free set of this cardinality. Can it be done something better? That's the question you are asking. Okay? Can we do it better? And the answer is it cannot be better, which comes from another different area of again additive number theory. And therefore, let me insist. Again, you just want to use it here and go to sum free and just state the results. Okay? Suppose I take a set A and another set B in integers, both finite set, of course. And I define A plus B. I could have normally defined little a plus little b, but let me put it in a slightly different way. Any n where n can be written as a plus b, a in a. Okay? This is by a plus b. When I add a and b, it is a set of integers n, that is n can be written as a plus b for some a in a, b. Okay, why did I do this convoluted things instead of saying just a plus b equal to little a plus b? The reason is when you write a plus b as little a plus little b, then I have to say whether it is counted with the multiplicity or without multiplicity. Okay? Because the same integers can appear as an element of a plus an element of b more times, more than one time. Okay? I want to insist that I am counting it without multiplicity. And since I want to insist that I am doing it without multiplicity, I have to be very explicitly how I am defining it. And therefore I am defining it as a plus b is those integers n which admits at least one representation as a plus b. Since now I am counting without multiplicity, it is perfectly possible that a plus b will have a cardinality with this form. Theoretically. And now the theorem. Cardinality of a plus b cannot be very small. Cardinality of a plus b is at least as big as cardinality of a plus cardinality of b minus 1. Okay? Cardinality of a plus b equal to cardinality of a plus cardinality of b minus 1. And this probably you should try as an exercise. Therefore, let me give you the exercise. Equality holds if and only if A and B are arithmetic progressions with the same common difference. This is an exercise. That if A and B are arithmetic progressions with the same common difference, then cardinality of A plus B equal to cardinality of A plus cardinality of B minus 1. And conversely, if cardinality of A plus B equal to cardinality of A plus cardinality of B minus 1, then A and B are arithmetic progressions with the same common difference.
One doesn't get to see these such exercises in an elementary book on set theory. Should have been there. I have seen it.
Okay, yeah. Yeah, but this is not about it. This is something special for integers.
Exactly.
Yeah. And now, another theorem. This is the theorem that you want. Suppose the G is a group Z over T. And again, A and B are subset of G. Okay? If A and B are subset of G and G equal to Z over P Z, then what can you say the lower bound for A plus B? Okay? What can you say A plus B bigger than or equal to? Now we are in a finite abelian group. Okay? And the point is that an analogous theorem is true with some rider. What is the rider? If A and B are both in the set over Pz, A plus B cannot exceed. A plus B is also a subset of set over Pz. Therefore, its cardinality cannot exceed P. Whereas this number can be theoretically bigger than P. And therefore, now the theorem is cardinality of A plus B is bigger than or equal to minimum of P and the cardinality of A plus cardinality of B minus 1. Sorry?
The difference is that here you are looking at cyclic one and here earlier you were not necessarily.
I am looking at integers here.
Yeah.
No. Okay, sorry. I should have made it very clear. This is the theorem true for integers. A plus B is bigger than cardinality of A plus cardinality of B minus 1, where A and B are integers. It is easy to prove. Where again you can prove the equality holds when they are arithmetic progression. But that one is a little difficult to do. Because you know a finite, a cyclic group. And specifically Z or P set for that cyclic group, you cannot do anything better. Is that okay? Very surprisingly, actually in connection with the type of varying problem and other problems which I was talking about, it was proved first by Cauchy, and not being aware of Cauchy has proved it already. It was later proved by Davenport. And therefore, this is actually called as Cauchy-Davenport theorem. So, Cauchy-Davenport theorem is a theorem which says that if you have two sets A and B with the cardinality, then cardinality of A plus B is bigger than the minimum of cardinality of B, and cardinality of A plus cardinality of B minus 1. Okay. And normally, when you say XY theorem, you normally mean that it was a paper by X and Y. Okay? And therefore, as my friend Deshwe is interested in saying, that this is probably only theorem where the two authors were lived in different centuries. Okay. Now again, let's do one problem. For G equal to Z over P set, this is 10. In other words, if G equal to Z over P is 10, you see I have already produced a Humphrey set, namely the middle one third, and we have proved that the middle one third is a Humphrey set, and we were wondering whether there can be a bigger Humphrey set. Okay. And we are going to prove that for Z over P set, there cannot be a bigger Humphrey set. This is the fact. Okay. Let's prove that. Suppose A is a Humphrey set. Can you tell me 5 minutes before the allotted time so that we can stop? Okay? A is a Humphrey set. What does that mean? That simply means that when you take A plus A, it does not intersect A. That's all. I mean, when you say that A is Humphrey, which means that there are no three numbers x, y in Z, such that x plus y equal to Z has no solution there. Which is the same as saying that when you take A plus A and then A and the intersection is empty. That essentially means that the cardinality of A plus cardinality of A plus cardinality of A has to be less than or equal to P. Because you are in the group Z over P Z. In the group Z over P Z, you have two disjoint sets, A plus A and A. Therefore, their cardinality cannot be more than P because there are two disjoint sets. But on the other hand, by Cauchy-Davenport theorem, capital mod A plus A is less than or equal to, is bigger than or equal to minimum of P. That case I forget because that will not anyway come. 2 mod A minus 1. Therefore, this is 2 mod A minus 1 plus mod A is less than or equal to P. Which means 3 mod A is less than or equal to P plus 1. Therefore, mod A is less than or equal to P plus 1 by 3. Therefore, any Humphrey set can have the cardinality at most P plus 1 over 3 and not more than that. And we have already produced examples whose cardinality is around P plus 1 over 3. Is it okay? And now let's continue with this. Now ask the following question. Therefore, since I need this information, let me write that down. In this case, it is n over 3, this is 3 divides n, and n minus 1 over 3, and n plus 1 over 3, depending upon what makes them as an integer. That's the number of elements. Therefore, roughly n over 3. But not exactly n over 3. It is exactly n over 3 only when 3 divides here. And a little bigger than n over 3 if n is congruent to 2 modulo 3. And a little less than n over 3 when n is congruent to 1 modulo 3. Is it okay? Now I can ask the following question. I take a general degree. I have not even said that this is maximum summary set. Forget it. Okay? I have produced a summary set only for n equal to p. I proved it is maximal. Because only for n equal to prime, I can use Cauchy-Davenport theorem. For a general n, I don't have a Cauchy-Davenport theorem. Since I don't have a Cauchy-Davenport theorem, I don't even know this is maximal. Okay? Now I take a general group G, and then I would like to know what is the density of the maximal subtree set. Okay? What is the density of the maximal subtree set? I will give an algorithm to do that. Okay? The algorithm is you take a surjective map from G to Z over NZ for some n, whenever it exists. Okay, take a surjective map that Z over NZ. And here I know the maximal subtree set, which is the bit 1/3. And now take the inverse limit. Okay, and once you have a surjective map, then the density will not change. Correct? Once you have a surjective map, the density will not change, and therefore this density is essentially 1/3. And therefore, this density will be essentially 1/3.
You're taking G again, G finite abelian.
Finite abelian group. Always, I mean, we are not doing anything about things. And in fact, there are a few good theorems on non-abelian group which I have been trying to study for the last 10 years and I have not done, and therefore you cannot ask a question on that. So abelian group is the only one that they understand.
And also finite.
Finite abelian group. The simplest case ever possible. Okay? Therefore, this is what we are going to do. Good. And now remember, n is at our choice. And therefore, obvious thing to do is choose that n which will have a maximal density subtree set and then go to inverse. Isn't it? That's an obvious thing to do. Because if it is to your choice, you choose that n, you will give you a maximal density subtree set and then go to inverse, the density will not change. And that means essentially we choose an n which is n plus 1 over 3. Therefore, you choose an n which is congruent to 2 modulo 3. Okay? If you choose an n which is congruent to 2 modulo 3, then the density is n plus 1 over 3. And that's what we will do. And again, there will be too many n's. Okay. First of all, such a funny thing will exist only if n divides the order of the group. Unless n divides the order of the group, you cannot get a surjective map from G to Z over NZ. Okay. And then there will be more than one n, which is 2 modulo 3, which is something. Which means, therefore, again, which is the n which will increase the density. The smaller the n, it will increase the density. Okay. Therefore, you should choose the smallest n which is congruent to 2 modulo 3, which you should choose. On the other hand, if there is even one prime n congruent to 2 modulo 3 which divides n, then the smallest number, smallest divisor would be obviously a prime divisor. Okay? If there is at least one divisor of the sum 2 modulo 3 which divides n, then the smallest divisor of n, which is on sum 2 modulo 3, is a prime divisor. That prime you take. Okay? But there may not even be one divisor of 2 modulo 3. Therefore, now you say the group is type 1 if there exists a divisor D dividing the order of the group, and then choose the P to be the smallest such a divisor. and then the density would be 2 plus 1 by 3. This is the so-called type 1 group. Now let's create the type 2 group, which is not type 1. If it's not type 1, then this doesn't work. Therefore, I should choose this. Therefore, choose n equal to 3. This is provided 3 divides ordinality. If 3 does not divide the ordinality, then that's the type 3. Where you should now choose that n which will maximize n minus 1 by 3n. The n which will maximize n minus 1 by 3n is the largest n. Therefore, you should see what is the largest n for which you can have the group Z over Z, and there is a surjective map from that. Okay? And then it is not difficult to see that n has to be really the exponent of the group G. Okay? And that is the maximal degree set. Okay? Now the next question is, okay, this is a conjecture. This is how all the things do come. Okay. Just I will finish in 2 minutes. Just no, I am finishing in 3 minutes. Then the other part I am not going to discuss. Is it clear? Therefore, when you want to do the maximum divisor, you take the G, go to Z over NZ for appropriate n, take the middle one third, that is free, take 1, and choose the n properly. And if there is a divisor congruent to 2 modulo 3, then that's the one which you have to choose, because that's the one which has a density little bigger than 1 third, and that you should also choose the prime P, which is a small super congruent to 1. If such a P does not exist, then you choose n equal to 3. And if that also does not exist, then you choose the exponent. So far, so good. Okay. That's a theorem. Okay. This is type 3. Now let me start with this. This is the theorem of Dayananda and Yap. This procedure gives maximal sum free set for type 1 and type 2. They do not deal that thing. Therefore, this gives you a procedure gives you a maximal sum free set from type 1 and type 2. Then this is theorem, which is Bentley and Ruja. Okay? Yeah, I don't even need a 5 minutes. No, I'm making the last statement. The theorem, which is Bentley and Ruja, to prove for type 1 and type 2, this is the only method to get the maximum. Therefore, if you want a maximal sum free set, the only method is to choose the n and then take the surjective map, take the middle one third, and take the inverse image. And again, you have a lot of choices. In the sense that this to Z over P set, there can be many maps. And then any other maps you can choose. And then take the middle one third, etc. Therefore, you have still choices, but this is the only method. And then for type 3, they proved this theorem. That this is, no, okay, sorry. Yeah, this procedure gives the maximal sum free. This procedure gives you maximal sum free. Okay? But whether this is the only procedure to get the maximum sum free? That's the question. Okay? And now the last sentence. Theorem. D. Surya Ramana and Jnana Prakash. this is not the only method to get maximum summary. All maximal summary sets cannot be obtained by this procedure. Okay? And then they also gave a procedure to get all the maximum summary sets. What's the procedure to get all the maximum summary sets? And with that I stop.
Anybody has any questions?
Just
Yes.
maybe a trivial question. You have in mind a theorem on summary sets which is valid for finite abelian but not for non-abelian.
No, non-abelian, not much is known, first of all.
But at
Because
least
now you have to say AB equal to C as a solution. AB equal to C may have a solution, but BA equal to C may not have a solution. You have to even properly define
properly defined, yes.
properly define what is it.
Questions
But
are-
there are results. But as I told you, my knowledge of those results is very limited. For example, people do mainly look at a special group like SL2, things which are little more, which occur much more frequently than any other thing. At least for number theories. SL2Z is, even if you don't look at the finite abelian group, the next obvious thing is to SL2Z modular forms and so on and so forth.
This is Surya Raman and Gyan Prakash from HRN.
And if there are no more questions, then I would like to thank Dr. Balaji. Very nicely delivered.
No, she can formally do it. You can do it.
Oh.
You just stand there.
Come from an institute, I think, to academic. आप यहाँ हैं। जी सर
Thank you very much. Thank you.
So
Yes.
next session is
That video. Online.
with that this session for Professor K. Singh Memorial Lecture comes to an end. I'm thankful to Professor K. D. Singh Madam and Professor Balasubramaniam Saab for completing this session, and especially Professor Balasubramaniam that he agreed to deliver this K. Singh Memorial Lecture. So now we are here to the first pre-lunch session, and that has to be chaired by Professor Sophie Saab. We have two lectures in this session. First is from Professor U.C. Dey. He is from University of Calcutta, West Bengal, and the other one is from Professor C.S. Arvinda Saab. I welcome Sophie Saab to carry forward this session.
So, I welcome you all to the first academic session after this wonderful talk by Professor Balasubramaniam. Yeah, so he has set the ball rolling, so we have to try to catch this the way he has presented his material. So it is a tough call on all of us. So we are going to have two speakers in this particular session, Professor U.C. Dey from University of West Bengal, Kolkata, and Professor C.S. Aravinda from Camp Bangalore. First speaker is UC Hiram. So he is going to talk about vector algebra and its applications. So that's a tough question because we were supposed to depart at 1:40 here. So maybe 2 o'clock is okay, half an hour. So half an hour will end at 1:25. It's 5 minutes. Okay. To begin with.
First of all, Namaskar. Thank you for your presence in my lecture. Also, I convey my thanks to Professor Pankaj Mathur and his team for organizing this conference and for their invitation in this. The topic is vector algebra and its applications. All of you know vector and its applications. You know from the college life. But I will say in a slightly different way. Vector can be studied from 3 standpoints. First of all, this is a problem. First is vector as a directed line segment. Directed line segment or a geometric vector Number 2 is vector as an element of a vector space. Vector as an element of a vector space. Number 3 is vector can be studied from transformation standpoint. In 300 BC, Euclid treated geometry as a logical system. And in 1637, René Descartes introduced coordinate system in Euclidean geometry. And according to his name, this Descartes, we call it Cartesian coordinate system. Due to his name, René Descartes, we call the Cartesian coordinate system. So coordinate coordinate. Some authors write this coordinate, and some are coordinate. Okay, what is the meaning of O and this ordinate? O is jointly, and ordinate means ordered, jointly ordered, coordinate. The British authors use this symbol, and some Indian authors who follow the books of British authors, they write in this way, coordinate. But this is the correct. This is the correct thing. All Russian, German, France, all the authors from these countries, they use this coordinate. This is the coordinate, not coordinate. Only British authors, they introduce this CO-coordinate. And we are Indians, they follow the British books, most of us. So we also write coordinate. Actually, this is the right thing. Next, how we will introduce coordinate system in Euclidean plane or Euclidean space. This is the origin, x-axis, y-axis. Axis means a directed line, only a directed line. So one thing, another. According to Euclid, a line is a breadthless line. A line is a breadthless line. According to Euclid definition, breadthless line. So if we say AB is a line, AB is a line, then what does it mean? This is actually, this AB is a line segment, not a line. This AB is a line segment. But this is also this line, this is the axis we take in this way. So this portion, we can say this is the half line. This is the half line, or sometimes it is said the half ray of the line, half ray of this line. Okay. So there is set of real numbers, ordered pairs of real numbers, R cross R. Suppose these points are A1, B1, ordered pair, A2, B2, etc. P is a point in the Euclidean plane. This is a plane. P is a point. Its coordinate is x, y. What does it mean? There exists an ordered pair of real numbers in R2. Conversely, if we consider an ordered pair of real numbers in R2, then there exists a point in the Euclidean plane. So there is a one-to-one correspondence between the points of the Euclidean plane and the set of ordered pairs of real numbers. And similarly for three-dimensional Euclidean space, we can introduce this thing. Mathematics, there are two divisions of mathematics, pure mathematics and applied mathematics. Pure mathematics is conceptual, some hypothesis, and from these hypotheses, some deductions. This is pure mathematics. Applied mathematics, some experimental facts. This is perceptual. That is, pure mathematics is conceptual, and applied mathematics is perceptual. But the development of mathematics, this indicates that the abstract concepts come from the practical problems. As for example, arithmetic comes from the problems of counting, calculus, geometry comes from the problems of surveying lands, and calculus comes mainly for the solve of the problems of motion. Vector algebra or vector analysis has its roots in physical problems, mainly to solve problems in mechanics, and later it has various applications in physical sciences. Developments of 19th and 20th centuries have resulted into the abstract concept of a vector and its interpretation. But the abstract concepts are difficult to the students, so they need real model or interpretation. The convenient geometric model of a vector, this is a directed line segment, not a line, not a complete line, directed line segment, say AB. Force, velocity, acceleration, etc. are physical quantities, but they have magnitude and direction simultaneously. Therefore, the physical quantities can be represented by a vector, and we denote this AB be a vector. Then A is called the initial point or point of application, and this is the terminal point, and we denote vector AB this. Sometimes this can be written as this direction. But when we are saying that AB is a vector, then there must be a direction, so no need to this arrow sign. No need of this arrow. And modulus of a vector is denoted by this AB. There are three types of vectors. Number one is free vector or affine vector. Affine vector. Number two is localized vector, or another name is this, localized, or I have forgotten the name. Number three is sliding vector. Free vector or affine vector. If a vector has no fixed position or have no fixed initial point or point of application, that is affine vector. Localized, that is if the position is fixed, that is initial point is fixed. If a force acts on a particle at a point, then that is an example of a localized vector.
You mean perhaps
Or bounded vector.
instantaneous?
Bounded, just a minute, bounded vector. I have used this, bounded vector. Who is asking?
No, I said instantaneous, perhaps you wanted to say.
Huh?
I was wondering if you wanted to say instantaneous for localized vector.
Localized vector, yes. This is localized or bounded vector. Sliding vector, if a vector can move, I will say with an example. If a vector can move in the line of action without changing its effect on a rigid body, such as there is a brick, rigid body. There is a brick. I am taking this force. This is moving in a direction, but this force is a vector, but this vector shifted from this point to this point, shifted. So this is an example of a sliding vector. Achha, equality of vectors, collinearity of vectors, you know all these things. I am not going in that part. Projection of a vector. Projection of a vector on an axis. AB be a vector. This G is an axis. We are taking two planes, alpha containing this point and this, which is orthogonal to perpendicular to this axis, and beta is another plane containing this point and perpendicular to this axis. Then we get a point of intersection such that A dash B dash. Then the value of A dash B dash, this is called the projection of the vector AB on the axis G. Angle of inclination. We are taking two half planes. Suppose AB is a vector and G is an axis. We take a point P. We take half line parallel to this vector, this axis, and another half line parallel to this AB vector. Then this angle is called the angle of inclination. Then what is the coordinate of a vector? Suppose AB be a vector. Then the coordinates of a vector is the projections of the coordinate axis. That is x-axis, y-axis, and z-axis. If we write this, the coordinate x, y, z, this means this projection of this vector on this is x-axis, this is y-axis, this is z-axis, three-dimensional. This is not, we cannot consider this thing, this board we cannot consider for E3. We cannot use this. This is if there is a vector, this space is a vector. The projection of this vector on the x-axis, y-axis, and z-axis, vectors are this x, y, z. That is called the coordinates of the vector AB. We can write projection of a vector on an axis. This is equal to the modulus of the vector AB into cos theta, where theta is the angle of inclination of the vector with respect to the axis. Okay. If we consider three-dimensional Euclidean space, we take three vectors I, J, K, x-axis, y-axis, I, J, K, x-axis, y-axis, z-axis, I, J, K are three unit vectors. Then we can write any vector in the linear combination of xi plus yj plus zk if the coordinates of the vector AB is x, y, z. Now scalar product of two vectors. Suppose alpha is a vector, beta is a vector. Then alpha dot beta, this you will know very well. This is equal to cos theta. What is the physical interpretation of scalar product of two vectors? Scalar product of two vectors is the work done by a force on a particle. If we take this force as a vector F on a particle, this can be written as F dot displacement of the particle by the force. This is D, F into D. This is the scalar product. Also, multiplication of a vector by a real number. Suppose A is a real number, then A alpha means A alpha is the same vector as alpha, but direction may be changed. If A greater than 0, then same direction if we take alpha in this direction, for A greater than 0 this direction, otherwise for A less than 0 opposite direction. Also difference of two vectors, addition I have told. For addition of two vectors, please listen. I will say important things. Wait. There are two rules, triangle law and parallelogram law for the addition of two vectors. Triangle law, alpha is a vector, beta is a vector, then alpha plus beta is this triangle law. Parallelogram law, this is alpha, this is beta, this is parallel to this is a parallelogram, the resultant, this is this diagonal, so not resultant, the diagonal is the addition of two vectors, alpha and beta. Simon Stevin, a Dutch scientist, Simon Stevin, so far I remember, this is 48 to 1620. Simon Stevin, he experimented with two forces. And to replace the force, he tried to replace the two forces by a single one, which is called the resultant of the forces. And he proved that the resultant of the two forces is the diagonal of a parallelogram, whose adjacent sides are these two forces. Similar result has been proved by Galileo. Galileo in the year 64 to 1640, this was Simon Stevin. He also proved the same thing. So, prior to the invention of vector concept, about 2 centuries before, these two scientists, they developed the sum or addition of two vectors. How it is possible, I do not know. Vector concept had not come at that time.